So today we're going to be looking at points of inflection, what they mean from one graph to the next, and how we can calculate them in a more exact way than just kind of pointing to a general area. Now, what is a point of inflection? A point of inflection is where the graph changes concavity from a point on the graph. Let's take a closer look at this. From concave up to concave down. Somewhere in between those two graphs, I have something that looks like an upward facing circle or an upward facing curve and a downward facing curve. That's what we mean by concave up and concave down. And the point between them where it changes from one to the other is what we call the point of inflection. And that point of inflection is directly between those 2 points. Now, if we look at this general curve, I think this is like a sine wave that we're working with here. We have a couple points of inflection. I have one here, and one here, where we can see the fact that my graph has concave up, concave down, concave up, and concave down. So every time it changes from one to the next, I have a point of inflection, which indicates where that change happens. So let's take a look at the derivative of this graph. So we notice that, first off, at the derivatives, the maximum point can be traced down to a 0 on the derivative. Now we'll notice that the zeros have 2 different types of zeros, and we'll actually talk about that later on. I have decreasing zeros and increasing zeros. At a maximum point on the graph goes from a positive slope to a negative slope, which means the derivative goes from a positive value to a negative value. At a minimum point, the graph goes from a negative slope to a positive slope. So the graph, quite literally, of the derivative goes from negative to positive. And so as we trace these down, what we notice is that directly between these points of concavity, the maximum minimum, directly between there, we have a new maximum point, which conveniently is right at that point of inflection previously. And we already know that because of the first derivative, it will tell us where that maximum point is and where that minimum point is because of where the zeros intercept. So if we trace that maximum of the first derivative down, I get a root or a 0 on the second derivative graph where the original change happened. I can trace that all the way down. In fact, I can take this derivative and trace it all the way back up. I can say, hey, this must have been for this going from negative to positive, must have been a minimum point on the first derivative, which means that that was a point of inflection on the original graph. So let's trace it directly up. Directly up. This, because it went from negative to positive, must have been a minimum point on its higher function. And then tracing that all the way up, it must have been a point of inflection on its higher graph. So boom. And that's what we're going to be finding here. So let's do a little bit of practice. Let's take a look at number 1. Now our goal on number 1 is to sketch the first derivative and then use that to sketch the second derivative because we're just getting used to what these graphs look like. And we're going to use this general rule. It looks like we have 1, 2, 3, 4, 5, 6, 7, 8 value points with 4 tick marks between them, so each one's worth about 0.2. We're going to label any critical values that we find here, and we're going to use that to graph our first derivative. So let's go through and let's do exactly what we just did. I'm going to take our maximum and our minimum points right here, 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 and here. And I have x equals 0, 2, 4, 6, and 8. Those are my critical values. I'm going to use those to graph my first derivative. I know at those points I actually have a 0, a 0, a 0, a 0, and a 0. And now I need to look at what's going on. Now, we noticed that this had a ruler. The idea really behind the ruler is just so we can actually trace. At this point, my first derivative is going to be 0. What I notice is that as I trace my slope to my next point, my graph gets very negative. And right about at that point there, my graph is as negative as it will be before I start curving back towards 0. And so that means I'm coming back up. At this point, I'm going to curve positive, so I'm going to come up over the graph up until about midway, where I start slowing down so I can hit that next peak. So what that means is that I'm going to curve up and down. And now I'm going to do this between each one of these. I'm going to be in the negative area all the way up until I hit 0, so I have to curve back. I'm going to be a positive slope all the way up until I hit that next maximum. Awesome. So I have that, and that is the graph of my first derivative. And then I'm going to do it again. I'm going to find those critical values and say, okay, x equals 1, 3, 5, and 7. I'm going to use those points to graph this. So add 1, 3, 4, 5, 6, 7. Looks like I have a negative slope, so it's going to start in the negative. Positive slope all the way until it's the next 0. So it's going to stay positive. Negative slope all the way until the next one, so it's going to stay negative. It's going to stay positive, and it's going to stay negative. Awesome. And so my final points right here, I have a critical value again at what looks like 0, 2, 4, 6, and 8. I'll notice specifically with the sine graph, the critical values of my second derivative are the same as my first, but not really too worried about that. But what we do know is that these roots, and let's do this root in blue, where it hits 0, these are going to be where the points of inflection are on our original graph over here. So let's list these points of inflection. I have it at x equals 1, 3, 5, and 7. And if I come all the way back to my first graph at 1, 3, 5, and 7, I see the fact that is exactly where my graph changes concavity. So boom. We have the first two derivatives, which are going to help us find, especially this, where it's going to help us find mathematically where those points are. But now that you've seen it done once, why don't you go ahead and try out number 3. Take a look at this function, graph its first and second derivative, and find the zeros of the second derivative to label exactly where those points are on the first one. Pause the video, unpause it when you're done, and see all you did. Okay, so let's take a look. Now, what we're going to do is we're going to do the same approach and same colors as we did on the first one. I'm going to list my maximum and my minimums. Not sure about that one. It looks like it's pretty flat, so we're going to go ahead and include that. But jury's still out on that one, which means that it roughly 0.6, 2.2, 3, 4, 6, and 8, I have critical values. So over here, I'm going to draw zeros at these numbers. So 0.6, 2.2, 4, 6, and 8. And then I'm going to look at the slope and say, hey, what's going on with the slope? So the slope is negative until it hits that 0, where it becomes positive all the way up until it hits the next one. So positive, negative all the way until it hits this one, positive until it hits the next one, negative until it hits this one. Awesome. We're then going to use this and find its max or its mins. So this is roughly 1.4 to 3.2, 5.2, and 7.2. So I'm going to put those as my zeros on my second derivative. So 1.4 to 3.2, for 5.2, 6, 7.2. Take a look at the graph. So it's positive until it hits that point, where it becomes negative until it hits the next point, where it becomes positive and negative. And the last one, the graph is positive. Boom. So we get something that looks like that. And so let's go ahead and list our max and our mins, critical values. I'm not sure about those at this point, so I'm just going to list these middle three. X equals, let's see, this is roughly 2.2, 4.2, and like 6.4. And what I notice is that these critical values, again, because of the nature of this wave, are very similar to these, which means if I draw on these a little more technical, I'd probably get the same values, which means that yes, that should be a 0 and an 8. But again, we weren't too sure, so we just went ahead and excluded them. But let's take that knowledge, find these points of interest, where this graph hits 0, where mathematically we would actually prove this equals 0, find those points. Points of inflection are going to be at x equals 1.4 to 3.2, 5.2, 6, and 7.2. And we're going to translate those back. So we said 1.4, 3.2, 5.2, and 7.2. So 5.2, 6, 7.2. And so what we noticed is those are pretty good estimates, especially just for a hand sketch of where my points of inflection are on the original graph. Awesome. And so that brings us to a few others where we're going to explore, again, the different types of zeros a little more in depth and just kind of get a little more practice on sketching these derivatives. So let's take a look at the first one. So the first one, we look at this graph and we see the fact that I have a point right here, which we know means that we can't find the derivative. It's not differentiable. Why is that though? Well, because at this point, my slope suddenly changes. All the way up until this point, my slope is a constant negative number. If I trace it with a ruler, the entire slope is a straight line, which means it never changes. So this part of my graph is going to be flat, and it's a negative number. So all the way up until about 4, it's negative, where all of a sudden it flips, and instead of being negative, boop, it's positive. So for the rest of the graph, it's a constant positive number. So right here, we have a break in the graph. So our function doesn't work anymore, which is why if we have a point, it's non-differentiable, because at this point, we don't know what to put. We could put pretty much anything we want in between these and these. The graph jumps from here to here. Now, if I were to take the derivative of that, I would do the exact same thing. I would say, okay, what is the slope right here? 0. What is the slope right here? 0. What is the slope at that point? Well, technically, isn't that infinity? So I would have to suddenly have the graph shoot off towards infinity and shoot off towards infinity, which I know won't work because is it positive or is it negative? So I have to include this whole line, and we don't really know how to do that. So I guess we could put a point up here and a point down here. So the function is broken because it now has 2 outputs for 1 input. So not a function either. Cool. Number 6, a little bit more of a challenge. So what I want you to do is I want you to pause the video on number 6 and see if you can't work this one out. This is a kind of fun one to try and sketch out. Unpause the video when you're done and see how well you did. Okay. So at number 6, we said this was going to be a fun one. What we know is the fact that we have asymptotes in the original graph. which again is going to present us with a little bit of information that we're not familiar with just yet. So let's take a look at a few points. Let's take a look at, let's see, 0, 2, actually I should be putting these right here, 4, 6, and 8. Okay, so at 0, my slope is 0 because it is the minimum point of the graph. So I'm going to put a point right there. At 2, it's also 0 because it's the maximum point, minimum point, maximum point, and then minimum point. But how is the graph interacting between those? Well, from here to about halfway between the next one, my slope steadily gets more and more positive. It goes positive, 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 all the way up until at that point, it reaches infinity. So my graph is going to curve up towards infinity, and I'm never going to touch that. But then on the other side of the asymptote, I'm still at infinity, but I'm going to come all the way back down until I hit 0. So I come back down from infinity until I hit 0. And at that point, when I hit 0, let's see, I was positive, 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 positive. Now I'm going negative all the way to negative infinity. So I'm going to curve all the way down to negative infinity. Never going to make it there. But once I hit negative infinity, I jump over to the next piece, and again, I'm still at negative infinity. All the way up until I hit this point, where I zero out and I go back towards positive infinity. I don't reach it, but I start back at positive infinity, come back down, go back towards negative infinity. Negative infinity until I curve up. So we get this weird tangent cotangent looking shape. So then let's take this and let's graph our next derivative. So I'm going to graph, well, it doesn't really look like we have any true maximum or minimum points. I have a maximum point right here at infinity. So at 1, I guess I'd say, okay, if infinity is the maximum point, is my slope at this point infinity or is it 0? Well, I could look and see by the fact that on both sides of infinity, it is infinity, which means my graph should, at all points around this, be at infinity. So I'm going to put a point way up here. Same thing right here. On both sides, my graph is at negative infinity. So at what point does it switch from negative infinity to 0 back to negative infinity? We could almost assume that at 3, so 2, 3, it's just existing at negative infinity. 2 points over, it's back at positive infinity. 2 points over, negative infinity. And so the slope of this graph goes from 0 to positive infinity. Never makes it there. And then on the other side, oh, it's still at infinity, but now it's a negative infinity. All the way up until it hits that spot right there. Negative, 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 negative. It hits 0, and then it goes back to being negative, and it traces away all the way back down. Whoop. And so we see it chased after that spot. This is chasing after this spot, but it's not going to reach it. Back to positive. Back to negative. Back to positive. Boom. So we get ourselves almost what looks like the original graph. So when we have a secant or cosecant, we're going to oscillate over to this weird tangent-like function, and then we're almost going to flip right back to the original thing. So, fun stuff. Like I said, number 6 was an enjoyable one. So now that you've seen some of those, let's take a look at how I'd graph the derivative of something that maybe isn't a function at all. How about just the derivative of a circle? I know I can implicitly find that. So go ahead and give this one a shot. Pause the video, unpause it when you're done, and see how well you did. Okay. So now that you've had a shot, you might have struggled with, okay, I've got two different points on this function. I could look at the edge, and I know at this point I'm dealing with a type of infinity. So why don't I just say at 2, I'm dealing with a line that's straight up, but I don't know if it's straight up or if it's straight down. So what I'm going to do is I'm going to say, how about we split the graph into a top half and a bottom half, and we're going to trace both of those values out. So for the top half, I'm going to say, hey, that's a positive infinity. So it's going to start here all the way up until at 2 points later, it hits 0. Or at the peak of that function right here, I hit 0, and then I start going negative all the way until I hit negative infinity over here. Perfect. And if I trace the other part, I'm going to do this in blue. I'm again starting at my point, but instead of tilting up and tracing the up where I know it's positive infinity, I'm going to take that vertical line, I'm going to trace the bottom. Oh, never mind, that's a negative infinity. It's a downward shaping curve. So this is a negative infinity all the way up until it hits the minimum point, where then it switches from a negative to a positive curve, which means my graph then curves up. Awesome. So we have the first derivative of a circle. Looks like this. And then let's take the derivative of that. So now I'm going to take the derivative of the blue with blue and the derivative of red with red, so we can trace what happens to these things. So with my blue one, the derivative of it starts at, positive infinity. And it's going to curve all the way up until it hits this flat spot right here, where it flattens out. But then I'm tracing it again back towards positive infinity. So I get basically an infinity loop right here. And what I'll notice is the fact that the red one does the exact same thing. I start at negative, I flatten out towards 0, and then I go back towards being negative again. So negative infinity, hit the 0, go back towards negative infinity. Boom. And so the second derivative of a circle takes those tangent-like functions and switches then into something that looks like a secant or a cosecant popped around. And so there we go. Not a function because I have more than one output for the input, but cool things. And there we go.